Good morning, everybody. It's Evan Stammen here for Umaghloko, Making a Difference. Today we're looking at the fifth video in our chapter on calculus, and we'll be concentrating on the idea of gradients and tangents. Now, I want you to consider what would happen if I was in a car going around a corner, and let's say this corner had a curve. Let's say it was something like that. And we were in our car over here, and at some position in this car, we lost control of the car. Now, this car would go off the road in a straight line. If the car was further along the corner, it would go off in a slightly different direction. And so the direction that these straight lines are traveling in, because the car has now lost control, is based on where you were on the corner. Please note that these lines are all straight, these lines I'm showing you. And the length of these lines might indicate the speed you're traveling, considering that we normally slow down as we go around a corner. And so these ideas are what we're going to be looking at today in terms of what we're talking about with gradients and tangents. The first thing I want to tell you is that as we've been describing, given that we have a curve, let's change that to the pen. Given that we have a curve, okay, not my best curve, but let's say there's a curve, okay, and given that this curve is called f of x, okay, we are saying that its instantaneous gradient can be given by f prime of x. And we've talked in the previous videos about the ability to go to derive, in other words, work out, calculate using a shortcut or using the rules of differentiation, how to get the f prime of x, the derivative, from the original equation of the original function, f of x. Now, if this is the gradient of this curve, and it keeps changing as we go along, so for example, we know that over here it is positive, and over here it is negative, and over here it is positive. And we can see it's getting steeper, which means that it's becoming a bigger positive, okay? Because the gradient is getting steeper, this gradient is increasing. What we are going to say today is if I was to look at a tangent to this curve, okay? So here is a line, and I'm going to draw this as a tangent to the curve such that it just touches this curve, okay? Such that I now have this line y equals mx plus c. Okay, so this blue line is y equals mx plus c. Well, we've discussed the problem that we had with this word gradient before, because we used to mean average gradient, and we use it so comfortably with straight lines because the m value was our average gradient, because on a straight line, the gradient is unchanging, it never changes, it's constant, and the gradient of this line is m. So the gradient of the blue line, and in this case, whether you talk about the instantaneous gradient or the average gradient is immaterial, is m. So whether you're talking about the average whether you're talking about average or whether you're talking about the instant gradient for a blue line, it's the same thing, okay, because it's a straight line with the gradient unchanging. But the gradient of this blue line is m, whereas the gradient of the black curve is f prime of x. Now, what happens at this point of tangency, and this is the key to our argument here, is hopefully you can see from the quick sketch that here the graph, the black graph's gradient is too steep. Here it is flattening out. Here it is becoming negative, so it's definitely going to be different from the blue gradient. And here it is changing again. But at this point of tangency, and this is the key, okay? So at the point of tangency, the blue gradient of the tangent and the green gradient of the graph, and here I mean the instantaneous gradient, okay? That at this point here, these two gradients, in fact, are equal. So in other words, if I was able to work out the gradient of the curve and to substitute in the value of a point, in other words, to substitute in an x value, that value I got out would be the m value of the tangent. So the gradient of the curve at a particular point, at the point of tangency, is the gradient of the tangent. In other words, if I was to draw in a different tangent, this time I'm going to, let's say, for example, draw one in yellow. If I drew in a tangent at a different point, let's say I drew in a tangent at this point here, okay, all I would need to know is I would need to know the point of the x value of this point of this contact point. Okay, I would need to know this x value. Okay, the y value is not actually all that important. I need the x value to work out the gradient of the curve, and the gradient of the curve would give me the gradient of the tangent. Okay, so again, that is, as we can see, as this curve moves around here, as this point moves around here, this tangent will move as well, and the gradient or the slope of this tangent will change as the point of contact moves left or right along the graph. Again, there are some nice pieces of software, Desmos and GeoGebra, which look at that, and I would encourage you, if you have access to a computer, to look at either GeoGebra or Desmos. These are online graphing graphing options to look at GeoGebra or Desmos to show you how that works. Okay, what I'd like to look at now is our two exam questions coming from old exam papers. And the first one is, what is the equation of the tangent? Okay, sorry, let me quickly bring this a little closer. Determine the equation of the curve. So I want to determine the equation of the curve. Sorry, the equation of the tangent to the curve. The curve we're looking at here is f of x equals x cubed, x cubed minus 2x squared minus x minus 2x squared minus x plus 2 at or where x equals 1. Now, let's go through our thinking here. We know that a tangent is a straight line, and so we know that it's going to have the form y equals mx plus c, and we know that our two goals are to find m and to find c. We normally find c by substituting in a point. But we find m, well, we normally find m by doing such things as knowing it's parallel to something, or knowing that it's perpendicular to something, or maybe knowing 2 points. But knowing 2 points would give me an average gradient. This time round, what I'm going to choose to use, which is, again, the point of today's lesson, is I'm going to choose to say that m equals f dash of x. So, to achieve my first goal of finding m, first I need to find f prime of x. And again, we don't need to do it by first principles. We can do it by our shortcut. So what we're going to do is we're going to apply our rules, which is to take the power to the front and to drop the power by 1. Now, the good news is that in this context, the questions are normally quite straightforward. They won't involve surds or funky denominators too often. They normally are focusing on the concept of m equals f prime of x. So minus 4x minus 1. Don't forget that the gradient, that the derivative of a constant always is 0. So we know that this point here would be plus 0 if we needed to, or that this term would derive down to plus 0. However, we know that we are talking about a particular point, so we need to have this derivative at the value x equals 1. So we're going to get 3 minus 4 minus 1, which in this case equals minus 2. And the key to that is that this value equals m. And so here again, stressing it again, this is the key. F prime of 1, okay, we're talking about at the point x equals 1 equals minus 2. Okay, so again, now we just go through our normal steps. So we now know that y equals minus 2x plus c. Now, our second part of our step here is to do what we've done in other cases before. We now need to substitute in a point. A point always involves an x and a y value. The problem we have is we don't have a y value, but we should know that y equals f of x. So we need to find it at x equals 1. So we look at f of 1, and f of 1 here would be 1. Now don't forget to use the original equation. 1 minus 2 minus 1 plus 2. So it just so happens that in this case, f of 1 is 0. So the point we're talking about here has an x value of 1 and a y value of 0. So we are going to substitute that into our partial equation that we've got so far. So we were halfway there by knowing m. Now we've discovered c, so we're going to substitute in our value. And so as a result, we're going to have 0 equals minus 2 times 1 plus c. And so we're getting that c equals 2. And we have a final answer of, in this case, y equals minus 2x plus 2. Okay, now this question, while it may be slightly complicated to you as you sit here right now, should actually become second nature to you, and you should see this as being one of the easier questions that you encounter. Okay, there is a routine to it. You need to find the derivative and substitute in the x value to find m. You just take the original equation and substitute in the x value to find y. That will give you a point with an x and a y value. You will substitute that in and find c to complete your equation, and there is your answer. Okay, this question does come with a second question, and the second question here in this case was, so let's have a look here quickly. The second question in this paper was, cool, having done this, okay, so we've got this answer at the bottom here, which I'll rewrite in a moment's time. Okay, having done all this, the question now asks us, where 9.2, okay, calculate the other value or values. Okay, again, experience will teach you that there will be only one of them. Okay, and where this tangent intersects the curve, if any. Where this tangent intersects the curve. Okay, so what we have had here is we had a curve. Okay, it's a curve that's doing something along the lines of that. Okay, it is the typical cubic shape. Okay, it has this sort of S shape to it. We have found a particular tangent that does this, for example, and it's got a negative grade. Sorry, let's just try and draw it better than that. It's got a negative gradient. Okay, so we can see that this point here, at the point 1, okay, it does turn out that this thing has got a y value of 0, which is interesting. Okay, it tells us something about it. That at this point 1, 0, this graph has a tangent labeled y equals minus 2x plus 2. Okay, now again, we can hopefully see that if this graph was to continue, it would intersect the function f of x again. Okay, a quick sketch here shows us that it isn't a case of values, that there will be a single value where this happens. Okay, and we can go ahead and look for it. As before, how would you find an intersection point? You make the two functions equal, you make the two things equal to each other. So on the one hand, I've got y equals x cubed minus 2x squared minus x plus 2. On the other hand, I have got that this is equal to minus 2x plus 2. So minus 2x plus 2. We know that these things are equal because they told us that this is an intersection point. So again, because this is an intersection point, and because it tells us this is an intersection point, we know that these things actually are equal. Okay, so again, what I'm going to do is my traditional method of solving an equation. So I'm going to get everything equal to naught. So I'm going to get x cubed minus 2x squared. Again, hope you haven't made a silly mistake here. Okay, no, I haven't. Okay, plus x, and there's going to be 0 after that. Okay, the good news about this particular one that we can see here is that we've got a common factor of x. So naught equals x squared minus 2x plus 1, and naught equals x minus 1, x minus 1. So the three solutions that we're going to get are therefore x equals naught, x equals 1, or x equals 1. Okay, so we can see that these three solutions have given us, or these three factors have given us three solutions. Again, knowing that we had an x cubed function, should not surprise us then that we're getting three solutions. Okay, now what we should realize is that these two are linked to the question. Okay, these two are linked to the question. So therefore, this third value here, x equals naught, is the answer to the question we're actually being asked to find here, because it's a new value. Okay, we haven't had this value before, so therefore it cuts at x equals naught. Okay, now again, my sketch at the top there was to help me understand this question. I do know that the value we are achieving here, that this value here was at x equals 1, and supposedly this value here was at x equals naught, which doesn't make sense because my answer is to the right of my previous answer, whereas actually x to the naught should be to the left of x equals 1, but this was just a diagram for clarity. Okay, so I wanted to quickly talk about the fact that actually we should have known from our picture that because of this tangency idea, you can see this happening often again, because of this point of tangency, we are not surprised that x equals 1 twice occurs in our solution. Okay, so that when a solution occurs once, it is an intersection point, but when a value occurs twice, it is going to be a point of tangency. So again, we can actually see this working both ways. Okay, because there's a point of tangency, we get that solution twice. Alternatively, because we got that solution twice, we know that this is a value of a point of tangency. Okay, so this question, although it started out fairly simply, has led to some fairly important points. Sorry about the wordplay there. Has led to some fairly important points which we need to take further. I've got one further question that I'd like to look at right now. Okay, and that is this idea of, it's actually quite a hard question, I think. Okay, and it comes from an old exam paper. And so what it says here is f of x equals minus 5x squared plus 4x, minus 5x squared plus 4x. Okay, we want to find the numerical value of so we want to find the numerical value of the tangent at the point of f at the point 1 minus 1. Okay, that's the first part of it. And the second part of it is to show for which values of A and C, for which values of A and C will graph g of x equals ax squared plus c touch the graph f of x at x equals 1/5. Okay, so the first one is actually very straightforward, but it's the question B that interests me a little bit. So we want to find the numerical value of the, sorry, quickly, of the gradient of the graph, not the tangent. Okay, my apologies. Let's quickly just fix that. Of the gradient of the graph. Okay, so we know that what we're looking for here is the gradient of the graph is going to be f prime of x, and we know that we need to substitute in this x value. So that's my thinking. I'm now going to go ahead and do it. So for question A, we realize that f prime of x will equal minus 10x plus 4. Therefore, f prime of 1 equals minus 10 plus 4 equals minus 6. And that is my answer to question A. Question B asks me, I've got this curve, which it happens to be a negative parabola, okay, to the left, to the right, okay. So what I have here is my original function. Let's say that's my original thing, and here is my original parabola. So let's just get that a little bit better than that. Okay, so there is f of x, and they're asking me where will g of x just touch this curve. So it's going to sit here somewhere and just touch this curve. Okay, again, because g of x has got no b value, we know it's going to be centered on the x on the y-axis. We are asking for this to happen at the value 1/5. So what I need to do here is realize two things. Firstly, we are being asked to solve for a and c. So because we're asking to find a and c, two values here, we know that we must be dealing with a situation of simultaneous equations. Okay, so we must be dealing with a situation of simultaneous equations, which means I need two equations. Okay, and these are not the equations of f and g, these are the equations that relate to that point of contact. And the first thing I need to know is that at this point, these two things share an x and a y value. And the second thing I need you to know is that at this point of contact, these two things will share a gradient. So at this point of contact, these two things would have, for example, a common tangent. Okay, so they might share a common tangent. And as a result, we should be able to see that at this point of contact, okay, we should be able to realize that at this point of contact, f of 1/5 will equal g of 1/5. Same y values. And that's my first equation. And my second equation is going to be that f prime of 1/5, which is the same as the gradient, will be the same as g prime of 1/5. And so these two things will be equal. Now I'm running out of time, so let's have a look at this. Let's move on through this fairly quickly. Okay, so what you're saying is that on the one hand, for my first equation, okay, so for my first equation, I've got that minus 5 times 1/5 squared plus 4 times 1/5 is the same as a times 1/5 squared plus c. Okay, and that will give me one equation with a and c. Okay, so we can have a look at it quickly. What am I going to get? I'm going to get that, therefore, minus 1/5 plus 4/5 equals a over, sorry, I should have used a different color, a over 25 plus c. So that's going to be timesing by, so that's 3/5. So if I times through by 25, I'm going to have minus 15 equals a plus 25c. I hope everything's correct at this point in time. And for question 2, which is important, I first would need to find the derivative. So quickly, just having a look here, f prime will be minus 10x plus 4, and g prime, hopefully you'll agree with me, will be 2ax. So what I need to do is substitute in these points. So in this case, I've got minus 10 times 1/5 plus 4 equals g prime, which is 2 times 2a times 1/5. So I've got to times through, so I'm going to have to times through by 5, which means I'm going to have minus 10 plus 20 equals 2a. I'm going to get that 10 equals 2a, so 5 equals a. I've got my one goal, and having got 5 equals a, I can plug that back in here. And if 5 equals a, then I think I'm going to get that, therefore, so I'm now going to get that minus 20 equals 25c, so minus 4/5 equals c. And I've done what they asked me to do. I found the values of a and c. Okay, so there are some pretty straightforward questions involving tangents, and as you can see from this last example, there can be some fairly fun ones that involve, in this case, simultaneous equations and other ideas. Please just recall that at the point of tangency, because it is touching, the x and the y values are shared by the two functions, but also because of these things being tangential, they share a gradient, and that is the key fact of today's lesson. Thank you very much.